everybody, welcome back to Trigonometry. Today we're in section 3.3 talking about circular functions. In this section we will talk about circular functions, of course. We'll learn how to determine values of circular functions, and we will also learn how to determine a number with a given circular function value. All of this is going to feel very familiar to you because what we're doing is we're taking everything we learned how to do in section 2.2 and we're doing it again, but this time in radians. So let's go ahead and get to it. So first, let's talk about this term circular functions. So far in this course, we've spent a lot of time talking about the trigonometric functions, or the trig functions. Now, the circular functions have the same definitions as the trig functions, that is, the x, y, and r work the same way. But instead of thinking of a trig function of an angle measured in degrees, a circular function is a function of an arc length. And you say, well, we haven't talked about arc length at all, and we really haven't. But we did talk about radians in section 3.1. And remember that the definition of a radian is an angle whose terminal side cuts off one radius length on the circle. And so it turns out that on the unit circle, where the radius length is 1, the angle measured in radians and the arc length are the same thing. So when we evaluate the circular functions, it will feel exactly the same as it did when we were evaluating trig functions, only now we'll be working in radians instead of degrees. Look at all these circular function definitions, and you'll notice that they are exactly the same as our trig function definitions, except instead of talking about the sine of theta and the cosine of theta, we are now talking about the sine of s and the cosine of s. And the variable s just designates to us that we are now working in radians. Now, you already know this, but just as a reminder, we want to remember that the unit circle has a radius equal to 1, and so wherever the terminal side of your angle crosses the unit circle, there will be an xy point. And so the horizontal coordinate of that point represents the cosine, and the vertical coordinate of that point represents the sine. That is not new information. We've been knowing that since section 1.3, but I just wanted to remind you. So here's example 1, and it says find the exact values of the sine of 3 pi over 2, the cosine of 3 pi over 2, and the tangent of 3 pi over 2. And you'll notice that there's no degree symbol here. Of course, the pi symbol sort of gives away that we're working in radians, but even if we didn't see the pi symbol, we would have to assume that the number is in radians because there's no degree symbol. Now, since radians are still pretty new to us, the easiest way to evaluate the circular functions is going to be to convert your radians into degrees so you can have a visual representation of the angle, and then you'll be able to figure out the function value. So let's take our 3 pi over 2 and let's convert it to degrees. We recognize that pi over 2 represents 90 degrees, so 3 pi over 2 is going to be 3 times 90 degrees, which is 270 degrees. And now let's draw ourselves a diagram. So here's a coordinate system. The 270 degree angle would be right here with its terminal side on the negative y-axis. And so that means that terminal side is going through the point 0, negative 1 on the unit circle. And so we see right here the cosine and the sine of this angle. So we're going to write the sine of 3 pi over 2 is the y-coordinate of this point, which is negative 1. The cosine of 3 pi over 2 is the x-coordinate, which is 0. And the tangent of 3 pi over 2 would be y over x, which would be negative 1 over 0. But since 0 is in the denominator, that value is undefined. And now let's take example 2. And again, it says find the exact circular function value for each of the following. And just as a reminder, the word exact is kind of a clue for us that we will not be evaluating these on our calculators because we will want to keep irrational numbers in their radical form. So we'll start with the cosecant of 11 pi over 6. And of course, we want to convert 11 pi over 6 radians into degrees. So let's notice that pi over 6 is equivalent to 30 degrees. So 11 pi over 6 becomes 11 times 30 degrees, which is 330 degrees. And now let's draw ourselves a diagram. So 330 degrees, of course, is in the fourth quadrant, and it leaves a reference angle of 30 degrees. And now we didn't memorize the cosecant of 30 degrees, but we did memorize the sine of 30 degrees. So let's start by finding the sine of 330 degrees. This is a fourth quadrant angle, so the sine value will be negative, and the sine of 30 degrees is 1/2. So now we know the sine of 330 degrees is negative 1/2, and therefore we know that the sine of 11 pi over 6 radians is negative 1/2. But of course they asked us for the cosecant of 11 pi over 6, so at this point we just need to do a reciprocal. If the sine of 11 pi over 6 is negative 1/2, then the cosecant of 11 pi over 6 is negative 2. And let's move on to part B. So here we're looking for the tangent of negative 17 pi over 3. And so the first thing we want to do is convert this radian measure into degrees. And so we'll remember that pi over 3 radians is equivalent to 60 degrees. So negative 17 pi over 3 is equivalent to negative 17 times 60 degrees, which is negative 1020 degrees. Now, we have no idea off the top of our heads where to draw that terminal side, so let's just add 360 to that value until we get something positive. And so we see that negative 1020 degrees is coterminal with 60 degrees. So that's what we'll draw on our diagram. And of course we know that the tangent of 60 degrees is square root of 3, and therefore we know that the tangent of negative 17 pi over 3 is also square root of 3. And now part C, we're looking for the secant of 5 pi over 4. So let's take our 5 pi over 4 radians and convert that to degrees. We remember that pi over 4 radians is equivalent to 45 degrees. So 5 pi over 4 is equivalent to 5 times 45 degrees, which equals 225 degrees. And when we draw that on our diagram, we'll have a third quadrant angle, whose reference angle, of course, is 45 degrees. Now, we didn't memorize the secant of 45 degrees, but we did memorize sine, cosine, and tangent. So let's start by finding the cosine of 225 degrees. And that, of course, will be a negative value because this is a third quadrant angle. And we remember that the cosine of 45 degrees is square root of 2 over 2. So the cosine of 225 degrees is negative square root of 2 over 2. And now we know that in a minute we're going to have to find a reciprocal for this value because we were asked for the secant. And so let's remember that before this was rationalized, it looked like negative 1 over square root of 2. And so now, since the cosine of 225 is negative 1 over square root of 2, the cosine of 5 pi over 4 is also negative 1 over square root of 2. And so that means that the secant of 5 pi over 4 is the reciprocal of this value, so it's going to be negative square root of 2. So there's quite a little process that we're going through here, and it all is going to happen in your head eventually if you get where you're supposed to get. But look at what all we've put together. We learned in section 3.1 how to convert from radians to degrees. We memorized the values for 30, 45, and 60 way back in section 2.1. We learned about reference angles in section 2.2. So there are lots of moving parts here, and if you're weak on any one of those things, you'll want to go back to that section and review that so that you can have a good foothold here. Now, before we go on to the next slide, I do want to point out something useful to you. Notice that in every case, the denominator of the angle in radian form allows you to predict what the reference angle will be. So here in part A, we had 11 pi over 6. Well, pi over 6 is equivalent to 30 degrees, and 30 degrees was the reference angle. The same thing happened in part B. The original angle in radians was negative 17 pi over 3. Well, the degree equivalent for pi over 3 is 60 degrees, and 60 degrees was the reference angle. And then again on part C, we had 5 pi over 4 as our original angle in radians, and the degree equivalent for pi over 4 is 45 degrees, and that turned out to be our reference angle. So that's not a coincidence. That works every time. So when you look at the angle in radian form, you can right away see what your reference angle is going to be, and that can save you just a little bit of extra work and maybe help you prevent some careless errors too. Now we do have one more Quizlet drill, and this will be our last one for the course, but you have a Quizlet link in Canvas to help you practice these circular function values. And of course you're going to get some practice in the homework, but it's not enough for you to gain the skill that you need. So use the Quizlet link to drill yourself, and you folks that are taking calculus later on, the better you are at recalling these trig values, the easier certain sections of calculus will be for you. So really dig in and drill yourself and get yourself very proficient at evaluating these circular function values, and that will just set you up for success later on. And now let's talk about approximating circular function values. So of course, for angles that are not special angles or don't have special angles as reference angles, then we'll have to use the calculator to find those function values. And whenever you use the calculator to find a circular function value of a real number, just keep in mind that the calculator must be in radian mode. So you'll use that DRG button on the top row of buttons on your calculator, and you'll just select radians and hit enter, and look for the little radian indicator down in the lower right hand corner of your calculator screen. Okay, so if you've got your calculator in radian mode, let's just evaluate these. It's very straightforward, so I'm not even going to cut to the calculator here because you can enter them exactly the way they're written. You just need to be aware that your calculator needs to be in radian mode. So the cosine of 1.85 radians, you'll enter it just like that in radian mode, and it's going to be approximately negative 0.2756. Again, like I always say, when you're doing your homework in MyLab, look for instructions that tell you how many decimal places you have to keep. But here, in these examples, I'm just going to round off our function values to 4 decimal places. Okay, for the sine of 0.5149, again, you'll enter it just like it is, and that will be approximately equal to 0.4924. Now notice that when we work in radians that are in decimal form, the angles can look a lot like the function values. And so it's easy to get yourself confused, and you'll have to think a little bit more about which numbers represent angles and which numbers represent function values. I like to remember that sine and cosine both have to be between -1 and +1. And so that helps me stay on the right track a little bit. If I'm evaluating sines and cosines and I get a number that's outside that range, I know that I've done something wrong. So it's very reassuring here that the cosine of this number is a value that's between -1 and +1, and the sine of this number is, again, a value that's between -1 and +1. Okay, for part C, we're asked to find the cotangent of 1.3209. Now you don't have a cotangent button, but you know that this is just 1 over the tangent of 1.3209, so you can enter it on your calculator exactly like that, and you should get approximately 0.2552. And then for part D, we're asked to find the secant of -2.9234. Of course, we don't have a secant button, but we do have a cosine button, so we can write this as 1 over the cosine of -2.9234, and that should be approximately equal to -1.0243. So I did decide to come over to the calculator for just one thing I want to show you. If you have your calculator in degrees and you really want to stay in degrees and you don't want to change to radians because you're only going to do this one thing in radians, then there is a workaround. So notice here that I'm in degrees. So if I wanted to find the cosine of 1.85 radians, then I could just enter cosine of 1.85. Now if I hit enter at this point, the calculator is in degree mode and it will assume that that 1.85 is degrees, and it would give me the cosine of 1.85 degrees. But I can convince the calculator that I mean radians if I just use the degrees minutes seconds button here, arrow over to the R stands for radians. Okay, now I've told the calculator that yes, we're in degree mode, but I actually want the cosine of 1.85 radians here. And so when I press enter, I get the same answer that we got before. So that is an option for you. So, you know, if you're working on a test where you're having to switch modes back and forth, this might be an option that you want to take advantage of sometimes. Now here in example 4, we are kind of working backwards. So part A says approximate the value of s in the interval from 0 to pi over 2 if the cosine of s is 0.9685. So 0 to pi over 2, you know, is equivalent to 0 to 90 degrees. And so we're looking for a first quadrant angle. And you remember that whenever we know a function value, but we want to work backwards and find the angle, we have to use the inverse form. So let's restate this relationship right here in inverse form. If the cosine of s is this number, then that means the cosine inverse of this number is s. And obviously that's not a value that we have memorized, so we will have to use the calculator here to get an approximation. And at this point, you really have to pay attention to whether your calculator is in degree mode or radian mode, because it's going to give you the answer in whatever mode it is set in. Your calculator must be in radian mode. And so if your calculator is set in radian mode and you enter inverse cosine of 0.9685, you'll get approximately 0.2517. If your calculator is set in degree mode and you get the answer back in degrees, then you could just multiply by pi divided by 180, and that would convert to radians for you. Now in part B, we're asked to find the exact value of s in the interval from pi to 3 pi over 2 if the tangent of s is 1. Okay, so the word exact is kind of a clue to us that we will not be relying on our calculator here. We'll be using reference angles. And the interval here, notice, goes from pi to 3 pi over 2 radians, but in degrees that would be 180 to 270 degrees. So we're looking for an angle in the third quadrant. Let's go ahead and draw ourselves a diagram of a third quadrant angle. And now we will use this statement as a clue to help us find our reference angle. So if the tangent of our unknown angle is 1, that is one of our memorized tangent values, and that tells us that the reference angle is 45 degrees. So that would be right here. And if the reference angle is 45, that means the standard position angle in degrees is 225 degrees. But of course, when we're working with s, we really want to get into radian form. And also the clue here with the interval tells us that we're expected to give an answer in radian form. So we know that 225 is 5 times 45 degrees, which in radian form is going to be 5 times pi over 4. So the third quadrant angle that has a tangent value of 1 is 5 pi over 4. And here's example 5. It says find the value of s in the interval from 0 to pi over 2 that makes each statement true. Round answers to 4 decimal places. Okay, so here we have in part A, the cosecant of s is 1.0219. Now we've talked about this before, so of course you know that if we had an inverse cosecant button on our calculators, we could do this example the same way we did part A in the previous example, but we don't. So what we'll have to do first is restate this in terms of either sine, cosine, or tangent. So we know that cosecant is the reciprocal of sine. So if the cosecant of s is 1.0219, that means the sine of s is the reciprocal of 1.0219. So I'm just going to write it as 1 over 1.0219. I'm not going to bother to go to the calculator and get that decimal value, because if I did, I would have to round it off, and I don't want to create any rounding errors. So if the cosecant of s is this number, the sine of s is the reciprocal of that number, and now we can go to inverse form, and we can say the sine inverse of this fraction is going to equal s. and you can enter that directly on your calculator. Make sure that you're in radian mode so that your answer comes out in radians. And we would find that S is approximately 1.3634 radians. Now, I wrote radians here just to remind us that we're dealing with an angle in radians, but keep in mind that angles given in radians do not really need a label of any kind. And now I thought I'd just show you how to check this answer, because you won't always need to, but every now and then, like on a test, you might want to make sure that you did everything right. So what we just found is that the angle we were looking for was 1.3634. If that's true, then the cosecant of that angle should give us this number. So what we can do is just evaluate this on the calculator. And so the cosecant of S, of course, would be 1 over the sine of the number we think is S. And so when you enter this on your calculator, you should get approximately 1.0219. It won't be exact because we did do some rounding here, but it should be very close. And the number I got was 1.0218989 and so on. If you round that off to 4 decimal places, it does round to approximately 1.0219. And so that value checks out. And now let's look at part B. Here we're given the secant of S equals 2.3925. Now this is very similar to part A, so if you would like to pause the video and try it on your own, I think that's a great idea. And now I'll go through it with you. So we know that we don't have an inverse secant button on our calculators, so we need to restate this in cosine form. If the secant of S is this number, then the cosine of S is 1 over that number. And now we can go to inverse form. So the cosine inverse of this fraction is equal to the angle that we're looking for. And that turns out to be approximately 1.1396 radians. Okay, again, I'm going to do a check. So I'm just going to plug my 1.1396 back in here and make sure that it works. So the secant of 1.1396 would be 1 over the cosine of 1.1396, and that does come out approximately equal to 2.3925, and so that checks as well. And here's example 6. This is kind of the same idea, but in example 6 we are asked to find the exact value of S in the given interval. So in part A, they ask us to find an angle in the interval from pi to 3 pi over 2 whose tangent value is equal to square root of 3. Okay, now we've talked about this before, so you already know that the interval from pi to 3 pi over 2 would be the interval from 180 to 270 degrees. So we're talking about a third quadrant angle. Let's go ahead and draw ourselves a diagram. And now we know that the tangent of this angle should be square root of 3. This is one of our memorized tangent values, and so now we know that the reference angle is 60 degrees, so I'll put that right here. And that tells us that the standard position angle is 180 plus 60 degrees, which is 240 degrees. Now we do need to convert this into radians because our interval is in radians. So we know that 240 degrees can be written as 4 times 60 degrees. And then we know that the radian equivalent for 60 degrees is pi over 3. So our angle S is going to be 4 times pi over 3 radians. Now let's take a look at part B. This time we're supposed to find an angle in the interval from 3 pi over 2 to 2 pi radians, and the cosine of this angle is square root of 3 over 2. Now 3 pi over 2 radians is 270 degrees. 2 pi radians is 360 degrees. So the quadrant that goes from 270 degrees to 360 degrees, of course, is the fourth quadrant. Let's draw ourselves an angle whose terminal side is in quadrant 4. And now when we think about the cosine of S equals square root of 3 over 2, that's giving us the reference angle. Square root of 3 over 2 is one of our memorized cosine values, and we know that's the cosine of 30 degrees. So now we know the reference angle is 30 degrees. We'll put that on our diagram. Now you can see that angle S is going to have to be 330 degrees, but then to convert this to radians, we need to think of it as 30 times something. So 330 degrees is 11 times 30 degrees, and the radian equivalent for 30 degrees is pi over 6 radians. So 11 times 30 degrees can be written as 11 pi over 6 radians. Now, sometimes they can ask us to do what we just did in example 6, but the interval that they give you might cover more than one quadrant. So when that happens, we'll just adjust our process a tiny bit. What we'll do is we'll use the sign of the circular function value that they give us to determine what possible quadrants we're working with. And then, just like we did before, we'll use the number, the function value they give us, to determine the reference angle from memory, and then that will help us figure out the standard position angle in whatever quadrants we've already identified, and then we'll convert the angle to radians if we need to. So here's example 7, and it says find the exact values of S in the given interval that have the given condition. So in part A, our interval this time is from 0 to 2 pi, so that's all 4 quadrants. And we're looking for any angle S such that the cosine of S is negative 1/2. So first let's think about the sign of this cosine value. This is a negative cosine value, and we know that cosine can only be negative in quadrant 2 and quadrant 3. So let's draw a diagram for each of those. Here's a quadrant 2 angle, and here's a quadrant 3 angle. Okay, now let's use the 1/2 to figure out our reference angle. This is one of the cosine values that we memorized, and this happens to be the cosine of 60 degrees. So that tells us that the reference angle is 60. So we'll put that here and here. And now for our quadrant 2 angle, S would be equal to 180 degrees minus 60 degrees, which is 120 degrees. And for our quadrant 3 angle, S would be equal to 180 degrees plus 60 degrees, so that would be 240 degrees. Now, of course, we're expected to give the answer in radians. So to convert this to radians, we remember that 120 degrees is 2 times 60 degrees, and so that's going to be 2 times pi over 3 in radians. And for 240, that's going to be 4 times 60 degrees, and in radians, that's going to be 4 pi over 3. So now when you enter your answer in MyLab, they will almost always have these curly braces on the screen for you, and the instructions will say enter your answers in exact form, separate answers with a comma. You know that it doesn't matter what order you enter the answers in, but we happen to find them in order from smallest to largest here. So I'll just put 2 pi over 3, comma, 4 pi over 3 in the braces. And just know that when you're typing in answer boxes in MyLab, to get the pi symbol, all you have to do is type the letters pi and it will create the symbol for you. Now in part B, we're still looking for all angles in the interval from 0 to 2 pi, and this time the tangent of the angles should be negative square root of 3 over 3. So same process. Let's start by looking at the sign of the tangent value, and it happens to be negative. So what two quadrants can we have negative tangent values? That would be quadrant 2 and quadrant 4. So we'll draw a quadrant 2 angle and a quadrant 4 angle. And now let's use the square root of 3 over 3 to find the reference angle. So this number we memorized is the tangent value for 30 degrees. So now we know our reference angle is 30 degrees, and we'll put that on both diagrams. So that means the quadrant 2 angle is going to be equal to 150 degrees, and the quadrant 4 angle is going to be equal to 330 degrees. Now to convert these to radians, we think of each of these as 30 times something. So 150 is 5 times 30 degrees, and so in radians, that's going to be 5 times pi over 6, and the 330 degrees is 11 times 30 degrees, which is 11 pi over 6. And again, when you type those in MyLab, you'll enter 5 pi over 6, comma, 11 pi over 6. Now for part C, we're still working with an interval from 0 to 2 pi, but this time, instead of just giving us a circular function value, they've given us this squared value. So it says sine squared of s is 1/2. So we know that first we need to unsquare this value, and so we'll have to use the square root property that you might remember from algebra. If the sine squared of s is 1/2, that means that the sine of s is plus or minus the square root of 1/2. We have to have the plus or minus symbol here because we know that this sine value after it was squared was positive 1/2, but that doesn't tell us anything about the sine of s. It could have been positive, and when we squared it we got a positive answer, or it could have been negative, and when you square it you would still get a positive answer. So we have to consider positive square root of 1/2 and negative square root of 1/2. And I know you might be thinking, they asked us to find the exact values of s, but this is not a number that we memorized as a sine value. But it kind of is, it's just in disguise. So let's simplify this and see what we come up with. We know that we have a radical rule that states if you have a fraction under the radical, you can split that up so that you have a radical in the top and a radical in the bottom. And then in the top, the square root of 1 is just 1. And so now we have plus or minus 1 over the square root of 2. And when you rationalize that, you have plus or minus square root of 2 over 2. And now we recognize that as the sine of a 45-degree angle. So 45 degrees is going to be our reference angle. Now we have to think about what quadrants s could be in. Well, sine is positive in quadrant 1 and quadrant 2, so I'll go ahead and draw those two diagrams. And then sine is negative in quadrant 3 and quadrant 4, so we'll also have to draw those two diagrams. And so it turns out we'll have 4 answers here, 1 in each quadrant. Now in quadrant 1, of course, with a reference angle of 45 degrees, of course, that is the quadrant 1 answer. In quadrant 2, the reference angle is 45 degrees, but the standard position angle would be 180 minus 45, so that would be 135 degrees. In quadrant 3, again, the reference angle is 45 degrees, so the standard position angle would be 180 plus 45, which is 225 degrees. And in quadrant 4, with a 45 degree reference angle, the standard position angle would be 315 degrees. And now we'll just convert each one of these to radians for our final answer. So s is going to equal pi over 4 for the quadrant 1 answer. In quadrant 2, 135 degrees is 3 times 45, so that's going to be 3 pi over 4. In quadrant 3, 225 degrees is 5 times 45, so that's going to be 5 pi over 4 in radians. And in quadrant 4, the 315 degree angle is 7 times 45, so that's going to be 7 pi over 4. And that completes part C. And that also completes section 3.3 for us. Everything we've done up to this point has been just getting us ready for the rest of the course. Now that we understand reference angles and radians in the unit circle, we can go on and do other things with these trig functions that we couldn't do before. So this is kind of a breaking point in the course. I hope that you'll really dig into section 3.3 and get very comfortable working with the circular function values, because that's going to just set you up really well for the rest of the course. Okay, I'll see you next time in section 4.1.